All right, so today's lecture is on electrical power, and that's going to be in the objective list. That's objective C.1.D.5 and 6. So let's take a quick look at what those objectives are before we get started. And that would be these ones here. Oops, maybe it's going to be these ones here. So we're looking for expressions that relate current, voltage, and resistance to the rate at which heat is produced when current passes through a resistor. And the rate and heat is energy, right? So we're talking about the rate at which the energy goes from electrical potential energy into heat in a resistor. And not all resistors, all the energy turns into heat. Sometimes, if a resistor can be like a light bulb, in which case some of that energy gets turned into light. But in general, for a regular resistor that we put in a circuit, it's going to turn electric energy into heat, and the power is just how quickly that happens. And also the relationships for the rate of heat production in a resistor. So we'll have a couple different equations that we'll see for the electrical power. Okay. So what we want to ask first is what's going to happen to the electrical potential energy of a charge as it moves around a circuit. And this is basically the simplest circuit we can have. You'll see here, this represents a battery, right, in a circuit diagram. We haven't looked at a lot of circuit diagrams yet, but there's only a few different symbols that we need to know. This first one here with a long and a short line there, this is a battery. This would be the positive end of the battery. This would be the negative end. So say if you have a 6-volt battery, that means that this point here would be 6 volts of potential higher than this point here. And then connected from the battery, just a line represents a wire and an ideal wire with zero resistance. Even though that's not really the case, any real wire is going to have a small amount of resistance at least. And then the zigzag line here, that represents a resistor. All right, and that's basically it. So let me just label that. So you always see the same symbols. This is a resistor, and this is our battery. Okay. So we want to ask what's going to happen to, and we know that in a real circuit, it's going to be negative charges that move around, right? Electrons. But it's equivalent to what would happen if you had a positive charge moving around in the other direction. So, and it's a little easier to visualize if you don't have to always have minus signs going on in your head. So we're going to look at what happens to a positive charge as it moves around the circuit. What happens to its energy? We'll have it start from here at point A and go around to point B, C, D, and then back. So what happens to the energy? So as we go from A to B, right? What would happen to the electrical potential energy of a charge, a positive charge, moving from A to B? Would it increase or decrease? If we're going
decrease
from a point of low potential to a point of high potential.
Wait, are you saying the positive charge when it reaches the negative one? What was the electric potential?
Yeah, a positive charge moving from a lower potential here to a higher potential here.
It's gonna decrease the closer it gets.
Well, we've got we know that the change in potential energy is just equal to Q times the change in potential, right? That's basically how we define voltage or potential, right? It's the charge times potential energy. So that's going to be, so if we have a positive charge, so Q is positive, and delta V, right? If we're going from a low potential to a high potential, delta V is going to be positive. So delta UE, that whole quantity, is going to be positive. Right, and that's because really because your VF is greater than your VI. Right, going from here to here, you increase the potential, So delta V is positive, your charge is positive, so your delta UE, your change in electrical potential energy, is actually increasing. So it increases. The energy of a positive charge would increase as it goes from A to B, through the battery, basically, right? We're talking about a charge that's going from inside the battery, from the negative terminal to the positive. All right, do we see why that increases? Just looking at the definition of electrical potential energy.
Yeah, it makes sense.
So if that energy increases, where does it come from, do you think? What's going to get a positive charge to move from this end of the battery to that end of the battery? Any ideas or guesses?
Potential difference.
Well, there's a potential difference there, but what type of energy is being converted into electrical energy?
Oh, I see.
If it's just a battery, like a AA battery, or some kind of a chemical cell like that, it comes from the chemical potential inside the battery, right? So that's how those batteries work, right? We're basically turning the chemical potential energy inside of it into electrical potential energy. All right, and if it's a battery, sometimes if we get back in the classroom soon enough, and I think we will, we might use a power supply instead of a battery that we plug into the wall, right? And if it's a power supply, right, that energy comes from the energy grid, from the holes in the wall. Right, so it's basically where are we getting the energy to run our circuit from, right? If we're using a battery, that energy is coming from the chemical potential energy inside the battery. If we're plugging it into the wall, that energy is coming from either burning coal or nuclear or wind or natural gas or something like that, right? So that's where the energy is coming from to get our positive charge from this low point of potential to the high point of potential, right? That's the battery's job. That's the power supply's job. And now once the charge is up here, right, then it's going to continue around the circuit. So what about as the charge then moves from B to C? What happens to the electrical potential energy of a charge? And we're assuming there's no resistance.
Does it stay the same?
Yeah, so in that case, it's going to stay the same, right? There's no change in energy moving from B to C because there's no resistance there, so there's no change in potential, right? If you if you try to measure and with a voltmeter the potential difference between these 2 points, there's not going to be any potential difference. So there's no delta V, so also there's no change in electrical potential, right? So by the time the charge doesn't lose energy or gain energy, traveling along the ideal wire here. And then what do you think is going to happen from C to D? What's going to happen to the electrical potential energy of that?
It decreases.
Yeah, it's going to decrease. So from C to D, we can see that the potential energy decreases. And that's usually because, if you have a resistor, and this is oversimplifying it. Well, what do you think? What's causing that energy to decrease? What's happening to the charges flowing through the resistor?
Well, the charge's flow is being reduced because it's a resistor, and that's what it's meant for, right? So
well, the charge isn't going to the flow isn't necessarily going to be reduced because the current, when we talk about the current flowing through, the current's going to be the same throughout the entire circuit, right? That the amount of charge that passes any given point in per unit time is actually going to be the same throughout the circuit. So I think I know what you're saying, but we don't want to say that the flow reduces.
Yeah, I don't know the word that I'm supposed to use for that. I forget the word.
Well, the energy is going to decrease, right? And the potential difference is going to decrease, right? So we know from the battery that this is the low potential end and this is the higher potential end. And we know that going across an ideal wire doesn't change the potential. So that means we still have high potential over here at point C because it's at the same potential as the positive terminal. We have low potential over here at point D because that's at the same potential as the negative end, right? So we've definitely got a decrease in potential going from here, right? So we can say that, well, and we'll see why in a second, but we'll say that delta UE, which is Q delta V, is negative. I don't think I put negative. Because our final potential is less than our initial potential, in this case, going from C to D. And why that happens is because, and again, an oversimplification, the charge is going to collide with atoms in the resistor, and the energy of that charge is going to get transferred into atoms in the resistor, and it'll become basically internal energy or heat inside the resistor. So I'll write, usually because charges collide with atoms, or I'll say molecules in the resistor. So the UE, the electrical potential, becomes internal energy in the resistor. Right, the average molecule is going to have more, random vibrational energy after the charges go through it and collide with them than it did before. So that the resistor warms up, and that electric potential energy has been converted into heat or internal energy in the resistor. Or if it's a fancier resistor like a light bulb, it might have gotten changed into heat and light. Or if it's a resistor like a motor, might have gotten changed into heat and kinetic energy or mechanical energy. All right, so it's all about conservation of energy still, just like it always is. So what's really happened then? So let's take a look at the next. I guess we have one more section, right? We have to go from D back to A, and what's going to happen in D going back to A as far as
the same.
That's going to stay the same, right? So D to A, just like B to C, there's no potential change. So also no change in. Right, so what's happened as the positive charge travels around the circuit is the chemical potential energy ends up becoming heat or internal energy, let's say internal energy of the resistor. So chemical potential energy, and I'll say from the battery, or it might be from the power plant that's providing the electricity to the holes in your wall. But you're turning chemical potential energy from the battery into internal energy in the resistor, is kind of the net result of the charge flowing around the circuit. All right. So I'll pause for a moment for questions or comments on that piece of it, and then we're going to look at the question of what the power is, how quickly, what the rate of energy delivered is based on our, things like current and potential. So the other thing to look at is at what rate. I gotta make sure I'm not really looking at the screen as I do this. I want to make sure I got papers in the right spot. All right, that looks okay. At what rate is energy going to be delivered to the resistor? And you should already know, or hopefully already know or can remember, that the power, P, right, and this is power, is just the rate of change of energy. So du dt. All right, so let's see. Well, we're changing electrical energy here. So what's the rate at which electrical energy gets delivered to the resistor, which means what's the rate that electrical energy is changed into some other kind of energy in the resistor? Well, we can see what that's going to be because we know we have a definition of electrical potential energy, which is just the charge times our potential, right? So if I rewrite that a little bit as dq dt times delta V, is there another substitution I can make now? I think we have a definition. We've talked about what dq dt might be. What quantity is that? dq dt, right? Q is the charge. So this would be the rate of charge moving past a certain point in a given amount of time. What quantity is that?
It'd be the drift velocity.
Not the drift velocity. That would be, if you had like a dx dt, right?
Oh yeah, come on.
It's okay. It's one of the quantities that we defined in one of the last couple of lectures before the break. What's a amps is the unit? Yeah, amps is the unit for current, right? It's current.
Yep.
Right. Current is the amount of charge passing a point at a certain time, right? dq dt is the definition for charge. So dq dt times delta V is the same as current, which is I, remember, was a symbol for current, and the unit of that is amps, times our potential difference. Right, and that's the power delivered to a resistor. So power is equal to current times voltage. And that's a big, important result. Not a difficult equation to use, but an important one. And you'll often use this or need to see this in a couple of other forms as well. And we know that since after we defined resistance to be potential over current, we know that current is V over R, or delta V over R. So power, if we substitute this in for current, we get another expression for power that, in case we don't know the current, sometimes depending on what you're given, you'll need to use a different form of this equation. So if I substitute this in for current, I get delta V over R times delta V, or potential squared over R. And another way to write it too is in this, since we know V equals IR, or change in potential is the current times the resistance, we could substitute this in for delta V here. and get yet another expression for power. So if we say IR is delta V, then we have I times IR, and power is also going to be equal to I squared times the resistance. And if you remember one of these, you can kind of quickly figure out the other ones, but it's good to have them all three of these forms written here because they all get used fairly frequently. Questions or comments on where we get these expressions for power delivered to a resistor?
No.
All right, well, we'll stop the lecture there for today. The next one will be on electromotive force.